Hello my steel design friends. In this video we're going to be looking at the Steel Construction Manual from the American Institute of Steel Construction. In particular, this will be the 15th edition. The Steel Construction Manual, or what is sometimes referred to as the Steel Bible in the US, has a lot of information and it can be very daunting to understand. So we're going to be exploring kind of how the book is set up over the next couple of videos. But in particular for today, we're going to focus mainly on Chapter 1, which is the geometric properties of the steel shapes and the designations that are used to represent specific shapes and how you can understand that. So without further ado, let's get started. So as you know, steel shapes come in a wide variety of shapes and sizes, literally. And there are different designations given to different members that represent something specific. So I'm going to kind of run down some of the more popular ones that you'll start to see. Okay, so the first one that we have is what we call the W section, okay, or the W shapes. Okay, and you might see something like, W10X33. Okay, and what this does, this is a very specific piece of information that if I flip to Chapter 1 of our book and go find our W shapes, the way that this is organized is you can see that these are the W shape tables and the properties and things that come out of those. Now I'll zoom in here in a little bit. Let me get to the right page. We're looking for a W10 by 33, so I'm going to be looking down this side of each of the pages until I can find the 10 by 33. They're ordered from largest sizes to smallest, and so my 10 by 33 should be on this page. Okay, kind of up near the top. So I will zoom us in a little bit. And then we will focus this a little bit more. Maybe. Okay, there we go. That's not too bad. All right, and so what you'll see is that each of these tables is set up in a similar fashion. The first thing to take note of is at the top of every table, there's always a diagram that looks something kind of like this. And this is kind of your map to what the information that they're giving. So here I've got it set up so that you can see our 10 by 33 is laying right here on this line. So it's a W10 by 33. The W means that it is a W shape. Okay, not the letter W, but it stands for wide flange. Okay, this is your typical, what we call, in the vernacular, an I-beam. And you can see why it's called an I-beam. It's kind of shaped like an I. It has a flange at the top, a flange at the bottom, and then relevant dimensions. And so dimensions that we use in design include things like the gross area. This is the A column. And so we can see that for a 10 by 33, fabricators that adhere to the AISC standard will guarantee within some certain amount of tolerance of maintaining these properties. And this standardizes the shapes between different fabricators. So whether I go to fabricator A or fabricator B for my shape, me as a structural engineer, I'm guaranteed a minimum set of certain properties that I've used in my calculation. I've got to have that. All right, so our 10 by 33 in this case has an area of what would be 9.71, this guy up here. Okay, the next one that's often that's very useful is this D dimension, which is the depth. And if you look at D, that's the distance from the top to the bottom, and that's how deep the beam is. Now what you'll notice in here is that a 10 by 33 has a depth of 10.2 inches. So it's not exactly that number, but it's close. And all of the ones that are in what we call the W10 family, if you look, W10s are all the way up here, and we come on down a little bit further. All throughout here, these families of W10s all are right around 10 inches. There's a 9.87 at the low end, and we get a little bit larger up to 11.1, but they're always kind of within that range of what we call the 10 family. Okay, now if you take that and compare it to, say, the 8s, which are on the same page right below, you can see that now they're running, 8, 7.9, 8.14, they're all right around 8. So the first indicator that you have in our label of this W10 by 33 that we had here is that this value right here is an indicator of the depth of the beam, roughly. That it is basically a 10-inch section. Now, it's not exactly 10, like we said, but it's close. Okay, the next value in this label over here, this is the weight per foot. So a 1 foot long piece of this W10 by 33 is 33 pounds per foot. So this is measured in pounds per foot. And a lot of the shapes that you see will be designated like this. So now, instead of having to record on a drawing, all of these dimensions that we're seeing in this picture up here, things like, there's a TF up here, this dimension here, stands for the thickness of the flange. We have a BF, which is the width of the flange. Okay, there's also a TW, this guy is the width of the web, and it varies from shape to shape, and that's what gives us our section properties. And so instead of having to go calculate moments of inertia or areas, by me simply specifying that I need a 10 by 33, I'm guaranteed to have an area about 9.71 square inches. I'm guaranteed to have a depth about 9.73 inches, and it saves me a lot of information even on the drawing. So you'll see, as an engineer, we'll label a beam as a 10 by 33. Or maybe it's a column that's a W12 by 50 something or whatever it is. It's a very concise way of representing a whole lot of information because of the use of this book and these labels that we have here. So all of those dimensions that I just listed, A, D, here's TW. Okay, we have our width BF is here, our thickness TF. All of these are the section properties that we have for these particular shapes. Now, one thing to note is that this looks like it has, it's built up of a series of rectangles. There are actually these rounded parts on both the ends of the flanges as well as where the web, which is this middle piece, connects to the flange. It's kind of a radius, if you will, that's created during the extrusion process when these things are hot rolled. Okay, and so there's a fillet that has to happen in there. And so the fillet information shows up here, these K factors. Okay, and you can see that the K to the bottom of the fillet goes from the top of the flange to the bottom of the fillet. And you get the same thing on the bottom. It goes from the bottom of the bottom flange to the top of the fillet as it starts to come around that way. That's the K dimension. Okay, and we need that dimension because if we ever need to weld a piece to the web, I can't do just a pure rectangle because the corner will bump into that rounded edge. We've got to actually cope it or cut a corner off to be able to do that. So those are all useful dimensions for helping us to do some of the detailing later on. Now, whether you're a steel detailer or a structural engineer, you do need to be aware of that particular set of information. All right, so that's all fine and dandy. Now, the part where this manual really starts to pay dividends is over in the computed properties page, which is on the next side. So if I look over at my 10 by 33 again, we're looking here, and I follow this line all the way across, and I go over to the next page, you can see that there's this number 33. This is a continuation of the line that we were looking at. Okay, now there are some things that you'll use for calculation. So for like beams and columns, when you're looking at compact sections, these two criteria will start to play a role, and these will be numbers that you'll pull out for a shape to learn about some of the section properties and the calculations that we'll show you in some of the later videos. Okay, over here we also have the moment of inertia, I. Okay, so that is the moment of inertia about the centroidal axis of our shape. Okay, now notice that this says with respect to the x-axis, so this is IX or IXX, depending on how you label it. The next guy is a section modulus calculator that we're going to use when we get into flexure that is also about that axis. This is basically I divided by, in this case, half of the height gets you this value. But it's a number that we compute often enough that they've gone ahead and tallied it to save you time for having to do that calculation. R is Rx, that's the radius of gyration, and then Z is Zx, which is the plastic section modulus, another flexural computation that you'll need. So we do that for the x-axis, which is, in this case, if you look at our picture, again, everything's back to the picture here. The x-axis is the horizontal centroidal axis. The y-axis is the vertical centroidal axis. It all goes through the centroid. Now, W shapes by nature are symmetric, so we know that they have to be in the middle. So all of these are being measured about the middle point of the cross section. All right, so we have our y-axis here, and then we get into some other properties that are used for torsion and things like that over here. J is the polar moment of inertia, Ix plus Iy, and then Cw would be a warping constant or something that you'll take a look at as well. Okay, or in particular, this is used in shear calculations and flexure calculations as well as that. So a lot of the pages, they're all set up that way. So, I mean, we can flip over to some of the bigger sizes. If we start to look, here we've got W21, so it's just a matter of finding where you are and then reading off the section properties. And so you'll be doing this a lot, playing around in this table 1. So that's our W shape, and that's kind of the way these are listed and why the way these are labeled here. Okay, you'll see some other shapes in there as well. We'll have S shapes. Okay, now the thing that we notice about that, if I flip back a little bit, we also have M shapes. S shapes would be back a page. Nope, wrong direction. There they are. I was off by a page. Okay, are these guys. And you'll see that, as you might expect, this also looks like an I-beam, but what this is a narrower gauge dimension. And so anything that is an S shape, they're also where what you saw with the W shapes, let me flip back a little bit. The W shapes, you see that the top and bottom of each of the flanges are reasonably parallel until you get to the fillet. Okay, for the S shapes, the top of the bottom flange is more inclined a little bit. Okay, so you have a flat bottom edge and then it kind of slopes up as it comes into the lab. And so again, there's some dimensional issues that you have to be aware of when you're starting to play with this. But otherwise, this table is laid out exactly the same. Okay, they give you the fillet dimension and so forth and so on, and the designator for that will be an S. That you'll know that, okay, it's a more of a narrower gauge I-beam, and it has its uses, and we'll talk about those, okay? And then, but it's the same designation. S24 means it's roughly 24 inches deep. See, we've got 24 and a half right there. And then the 121 tells you that it's 121 pounds per foot. Okay, and we like that number because that allows us to do estimation into cost. Once I know how much the steel costs per pound, I can very quickly tally up a grand total. And this will show up on drawings as like a bill of materials or a column schedule or a beam schedule or something like that. So that's what these designators start to mean. Every steel member that's fabricated in the U.S., somewhere on it has a stamp that will tell you what this shape is. You know, for my students, if you go look in KC254, the column that's exposed there, if you go look, you'll actually see a W8 by, and then its designation is on it. You can actually see it if you're curious and want to kind of see what that looks like. But there are different ways that different companies market. I just know that happens to be the one at our school. So, all right. So, but again, everything else is the same. Here's our nominal weight value, our compact section criteria, which we'll come back to, and then I, R, Z, and S are all labeled over on that one. So those are our S shapes done exactly the same way. All right, so if we flip a little bit further back, we then get into what would be, oops, too far. I lost it. There they are. Okay. We have what we call the C shapes. Okay. And so the C shape, what that stands for, anything with a C prefix is what is known as a channel. Okay. And the reason it's called a C is you can kind of see the shape, literally. That it's, something that kind of looks like that. And just like with the I shapes, the designation, you'll see something like a C12 by, oh, I don't know, 20.7, so it looks like a good one for us. Okay, so if we come down and we look at, so here's my C12 and my 20.7, you'll see that a lot of the top of the table is very similar. A, then D, then the TW, which is the web thickness, and then BF, which is the flange width, the width of the flange, and then the flange thickness is TW there. Okay, and so just by declaring that I have a C12 by 20.7, you can now come in and read off all the properties that you need here. And again, just like on the other shapes, my moments of inertia and section modulus radius of gyration of this base shape are all over here. Okay, and so that's kind of the designator that you will see for the channels. Okay, the next one that we have are what we call the L shapes. And those will be back just a couple pages past here. Okay. And as you can see, that's the L shapes that we have. Oops. Okay, will be what we call as an angle. Okay, and you'll see things like L4 by 4 by quarter. Okay, and what those designate is you've got to kind of, the designation on this has to do with, since angles don't have to have equal leg dimensions, the first one is the longest leg, the second one is the shortest leg, and the last number is not the weight anymore. This one happens to be the thickness of the angle. So to get the weight of an angle, you actually have to come in and look it up specifically out of the table. You can't tell by the designator. Now, a lot of shapes are common and used over and over. Let me flip over to my 4x4, which is a pretty common shape. Should be on that page. There he is. Okay, and so just like anything else, you've got this table. It shows you where the centroid is. As you would expect, the centroid of an angle is actually kind of out here in space a little bit. So now we've got, we have to have extra information that tells us where is this centroid located. Okay, and you'll see that over on the other page when I show it to you. So let's go look at our L4 by 4 by quarter. That's the bottom of here. Okay, and so we have, once again, this K dimension is that radius that we talked about. Inside this corner, there's a radius. Okay, so we need that dimension. We have the weight, weight per foot. Okay, we have the area, and then we get into some of the section properties associated with this. So for us, because these are what we, this L4x4, we're going to look at relative to the x-axis on this. We have the moment of inertia. We have the elastic modulus. We have the radius of gyration. Now I've got a y bar parameter. And what the y bar parameter is, if you look at the picture, is the distance from the bottom of the member up to where that x centroidal axis is located. Because now it's no longer in the mid-height like it was in the other. So this is where you can pull off the centroid of that location. So that's the y bar. And then we got plastic section modulus, and then there's another value as well, polar moment of inertia, and so forth and so on. Everything else is the same. Okay, now if we slide over, now we get into a y-axis calculation. And so 4 by 4 by quarter, and we come across and we have the exact same information, but now about that vertical centroidal axis. Notice that there's an x bar. Okay, and if we look back at the picture, our x bar dimension is going to be labeled from the left edge if the angle were oriented this way to the vertical centroidal axis. Now the thing that you have to be careful in all of this is that orientation of the direction of the angle. If this angle were oriented such that the short leg was coming out to the left, then you would have to flip and transpose all of these dimensions appropriately. Everything is measured relative to the back of the leg. Okay, so that's one little trick that you got to be careful of. Now, angles, as you might expect, are non-symmetric, and so there's actually a third axis, which happens to be one of the minimum or the maximum principal axes, would be this axis ZZ. Okay, and that's the angle that if you were is inclined something like this guy here. Okay, and so we get our I about that axis, our S about that axis, and then of course something about the tangent of that angle that kind of gives you the orientation of that axis as it's lined up. But you'll use that in in column calculations and things like that or unsymmetric bending type problems as well. So that's our single angle. So it is different. It doesn't have the weight directly in it, but that's kind of the way the table is set up, and you'll kind of start to see some of that. Now if we flip a little bit further back, where'd it go? If we go back into, say, I'm looking at page 1-114, we get into what we call the double angles. Okay, and so what will happen there is if you see something written as LL, let's say, 5 by, what's a good size? Go back a page. Yeah, 5 by 3.5. Say by yeah, we can just do 3/8. That's or slide up a little by quarter. Quarter works. Okay, it looks something kind of like this. Now we have an issue. So if we look at a 5 by 3.5 by quarter, what that means is that my angles on this, it consists of two angles, okay, that are separated by a gap on here, such that, and you'll see some nomenclatures such that, if I go, where is it? There they are. You'll see some nomenclature that looks like LLBB or SLBB. So anytime you see something that looks like this, what we write is LL. Sometimes you'll see this written as a 2L, which I think is the way AISC is going to write it. Yeah, so it's a 2L means that it's two angles together, 5 by 3 by, or 3.5 by a quarter would be this guy down here. Okay, but you'll notice that the section properties are now asking you, well, LLB or SLB. And what that has to do with, this stands for long leg back to back and short leg back to back. These are the back to back legs. So if we look at our shape on this, for our particular one, if it's oriented this way such that this dimension is 5 inches, okay, this would be the 3.5. That's the LLBB configuration. That the long leg of the dimension is oriented relative to that. Versus same set of angles in a pair, which now this is 3.5. Whoops, slide that up a little bit. This would be 5 inches. This would be 5 inches. That's the SLB to B orientation. So you can see the short leg and the long leg back-to-back dimension. Now, one other dimension that you have to pay attention to, especially on double angles, is this guy, this gap dimension. Because as I spread that further and further apart, I start to change the section properties. In particular, the moment of inertia with respect to the y-axis starts to change. Because the centroid of these is still down the middle of this. Okay, but that's the designation, and that's what it means. And all of that is tallied for you here. So you can see that, we've got our area. We have our long leg back-to-back, okay, and then we have things like the radius of gyration, ry, and this gap or this separation value here is the distance between them. So if you use the 0, it means that one angle is directly touching the other, whereas if I have a 3/8, that means that there's a 3/8 inch gap between them. This is useful for putting things like gusset plates and connector plates in between angles to work, and then it goes up to 3/4. These are fairly standard gap dimensions, okay, and then of course Rx is unaffected by that gap dimension, okay, and then you have the short leg back-to-back, the same thing happening here, okay, and so that's where we're at working with those. And then there's some more information over on the double angles on the other side, but for the basics, this is the kind of the nomenclature that we're looking at and what we're trying to work at on that, okay. All right, so that's that shape, okay. The last set of shapes that we have, oops, sorry for hitting the camera there, is what we call the HSS shapes, okay? And these stand for hollow shaped sections. Okay, and you'll find those back a little bit, back a couple of pages. If I go look at, I'm in table 112. That maybe we have a designator that is, let's find a good one. So if I come in and do HSS 20 by 20 by, we'll do a half on this. This is designated out just like we had with the angles. What these HSS sections are, this is a rectangular tube type section. Now, again, we've got fillets on the corners, so it's not quite rectangular. They got some slightly rounded edges on these, okay, and what they are is they are these dimensions. That this guy would be 20 inches, this guy would be 20 inches, and then this would be a 1/2 inch wall thickness. That's the designation that you would see here. Okay, so again, 20 wide, 20 1/2 inch thick. Again, we don't know the weight, but I can look that up on the 20 by 20 by half value here. That would be that second column again. So I'm looking here, this guy weighs 130.5 pounds per foot. So this is a monster tube steel section. Sometimes you hear them referred to as tube steels. Okay. All right. So that's now these are all HSS. This happens to be a square HSS, which means the sides are square. Okay. Versus say the rectangular HSSs, in which I can have different legs of different sizes on those. Okay. And so that's what we have. And so all the rest of this is pretty much the same as what we've been dealing with, moments of inertia and so forth and so on. So on. It should be fairly self-explanatory at that point, I guess is what I'm trying to say. Okay, all right, again, torsion constants over here. We have some workable dimensions kind of information. So that's kind of some of the basics for the shapes that we have happening here. The last one that we're going to do, and I don't want to go too much longer on this, is what you're going to see designated as a WT. Okay, and what this is a structural T shape that looks something kind of like this. Okay, so if we go find those are back a little bit. Those would be up on, say, I'm on 1-62 at this point, looking at these. And again, here's your map. It's a basic T shape. That's why it's called a WT. These designations are a little bit different. Okay, and in fact, they don't give you all of the section properties associated with some of this, because these guys are fabricated from W shapes. That if we look at the way that these are made, okay, is that the base shape of this thing, it's actually cut from a W shape that's twice as much, and it's cut in half here. And it's basically a half of a W, so that makes a T. And maybe I don't need a beam that's that stiff or whatever the reason that you want it, but everything else is still the same. This is still TF. This is still BF. okay, and this is still TW, and there's still a K radius happening here, and so forth and so on, but this would be a WT shape, if you will. So if we look at one, I've got a WT, let's see, how about a WT 10.5 by 46.5. Okay, that's the dimensions of the T section. So the T is roughly 10.5 inches deep, and it's at 46.5 pounds per foot in weight. Okay, this guy was made from a W21 by 93. Okay, and if you notice, this is half of that, and this is half of that. Okay, so if you ever need any other section properties that aren't contained on the WT page, you can always go back and pull those off of here. Recognize that the moments of inertia don't translate between them because dimensions change, but you know, some of the fabrication constants and tolerances and stuff will come off of this, so you'll see that. But that's what this WT stands for. It's a T shape made from a W section. Okay, and that's kind of what it stands for as we start to look on all of that. So anyway, that's kind of in a nutshell, kind of a quick breakdown of some of the shapes and the designations that we have. I hope it's made sense to you. We'll do a whole lot more with this manual, and we'll be coming back and forth into these pages, but you'll learn to get to know where these pages are. In fact, it's probably in your best interest. I haven't done it yet. Is putting in tabs for certain cases, particularly the angles. The angles are very commonly used. W shapes you can find pretty easy because they're at the front, but angles are only a couple of pages. The channels are only a couple of pages, so maybe you put an index tab on it to be able to flip to it, kind of depending on what your needs are at the time. Back in the day when I used to work in a consulting office, I actually had the common angles table, you know, taped to the wall beside me because that way I didn't have to flip the book open. But you know, those are all just kind of tricks for whatever it is that you're trying to do. So anyway, hope this made sense to you. If you got any questions, as always, leave us some comments down below. Make sure you subscribe to the channel, and we will see you guys next time. Have a great evening. Talk to y'all later. Bye. Happy engineering.